So the last lecture we were discussing about surface tension, and we had completed the topic of surface tension. In fact, going on to understand about contact angle and capillary rise. Okay, so now we come to the last part of these properties of non-ideal fluids, namely viscosity. I think today we should be able to complete viscosity, and next lecture this week, maybe we can keep some time aside for doubts and questions and discussions and things. And with that, we'll wind up this relatively simpler part of properties of matter, right? So right from elasticity to surface tension and viscosity, this is the portion called properties of matter. So we'll complete this, and then we'll move on to the next portion of physics, which will be oscillations and waves, starting with simple harmonic oscillations. So that's a pretty significant portion from your JEE point of view, as well as your 10+2 board syllabus point of view, both things. Anyhow, let's begin. So viscosity, this is the property of non-ideal fluids. As we discussed earlier, ideal fluids are both incompressible and non-viscous. So obviously any fluid which is having the property of viscosity comes in the category of non-ideal fluids. Okay. So viscosity is a non-conservative drag force that acts whenever there is relative motion within a fluid. So viscosity or viscous force, which is a non-conservative drag force, is the mechanism by which relative motion within a fluid tends to be opposed, okay, like kinetic friction in solids. And as a result, kinetic energy is dissipated. However, there are a couple of fundamental differences between viscosity and friction, which is why they are named in a different way, and the formula, etc., the mathematical expression is completely different. The similarity between friction and viscosity begins and ends with the fact that they are both non-conservative forces which tend to oppose relative motion and dissipate kinetic energy. But apart from that, they are not the same. They are very different forces. Okay? So the point of comparison between kinetic friction and viscosity or viscous force is only that much, that they are both non-conservative and they both tend to dissipate kinetic energy by opposing relative motion. Now, viscosity we will see in two situations. Okay. So viscosity, the first situation we'll see is in viscosity when a viscous fluid is in what is called laminar flow. So previously in hydrodynamics, we had studied about steady flow or streamline flow. And this is something different to that, which is laminar flow. Okay. So steady flow or streamline motion happens under a specific set of circumstances for an ideal fluid. Okay, steady flow cannot happen for a viscous fluid. The condition for steady flow is that first of all the fluid must be ideal, so it must be non-viscous. Okay, so hence there is no question of steady flow in a viscous fluid. Rather, the type of flow that happens in a viscous fluid is called laminar flow. Okay. And laminar flow occurs in such a way that layers of the fluid flow with relative motion with respect to each other, or you can say slipping with respect to each other. So in other words, we'll say that mathematically there is a velocity gradient.
Okay, sir. तो velocity difference होगा ना sir?
Yes, yes. So in other words, so we will understand in a moment what this means. Okay. So what happens in this case is that there is a velocity gradient within a cross section. So different points in a cross section are going to have different velocities, like we just said. Whereas this is the opposite of steady flow, that if you consider a cross section in steady flow, all points must be moving at common value of velocity. But here there will be a gradient of velocity. So in other words, there is a non-zero gradient. Gradient means rate of change with respect to position of velocity within a cross section. So just go through this section and make a basic note of the points. Then we will come to a more mathematical description of what is meant by laminar flow and what we mean by the term gradient of velocity in a laminar flow. Okay, so next thing we'll see is examples of laminar flow. So for example, if we have a situation where we have fluid which is flowing in this manner, that the velocity vectors can be represented by this kind of a diagram. That is, there is a gradient in velocity with depth. This is a side view of a cross section of fluid flowing along certain path. Okay, and if the velocity is like this, that is, there is a uniform gradient with respect to depth of the velocity. So this is depth and this is velocity. So you can see that an example of this is a fluid in motion along a horizontal axis. Let's say this is the x-axis with a uniform vertical velocity gradient. Okay, so as you go down, I've taken the y-axis downwards. Okay. So delta v by delta y is equal to some value. Like let's say this depth is totally h, and at the bottom here the velocity is tending to 0. At the top the velocity is v0, so it's v0 by h, where y-axis is downwards. So you can see here that the velocity is decreasing with depth. Like this. That is a slope is minus of v0 by h. So at any depth y, the value of velocity v is like v0 minus my, where m is this slope, which is minus v0 by h. Okay, so this could, for example, be the laminar flow along a straight canal along the x-axis and of depth h, okay, such that the top surface, what we are considering as y equal to 0, as v equal to v0, and lowest portion y equal to h as v tending to 0. So remember, so visualize liquid flowing along a canal which is along the x-axis, such that the bottom, so as you go down, the velocity of the liquid is decreasing because of the viscous forces which are tending to drag the liquid. So let's say you're creating some disturbance at the top, which is creating the liquid to flow at a uniform speed v0. But that liquid, instead of dragging the rest of the liquid with it with a velocity of v0, the velocity is decreasing as you go down because the liquid has viscosity. So there are drag forces involved. So in that case, the velocity gradient will be a uniform negative gradient as you go down. with depth, the velocity will be decreasing and decreasing all the way to tending to zero as you reach the bottom. So this is the most, like you can say, the most basic example of laminar flow, where there is a uniform velocity gradient with depth for liquid flowing along a horizontal axis. So the physical situation where you could be creating something like this is, just imagine you have like liquid which has a significant amount of viscosity, like you can say, water with a lot of suspended particles. Muddy water is an example of a highly viscous fluid. So suppose you have a canal in which you are creating some disturbance at the top by, let's say, rowing the oars of a boat or something. So the top layer of the liquid is forced to move at V0 because you're continuously pushing it with a set of oars. But that layer on top will be trying to drag the layer just below it. That layer will be trying to drag the layer below it, and so on and so forth. So the velocity will get transmitted from layer to layer, but not at the same rate because there is viscosity involved, which is dissipating kinetic energy. So there will be a gradient in the velocity. So the further you go down and away from where you are creating the disturbance, which is causing the motion in the first place, the lower your velocity will be, such that the layer of water which is in contact with the so-called bed or the floor of the canal is almost at rest. It's almost undisturbed. So that kind of an idealized situation will have a linear variation of velocity with depth. You can see it's a linear function. V versus y is a linear function. So uniform vertical gradient, that means that velocity varies with depth linearly. That's why the slope or the gradient is uniform. Okay, so let us come to the further understanding of this. Yes, viscosity is a material property of non-ideal fluids. Okay, so now within this laminar flow, if we consider a single sheet of liquid, so in that above example that I've taken, consider a sheet of liquid which is of surface area A and it is flowing with a velocity v because it is at a depth of y and its thickness is dy. Okay, so now when you see this in the side view, this particular sheet of liquid is flowing with a velocity v. The sheet of liquid just above it, which is in contact with it, will be flowing with a velocity of v plus dv. And likewise, the sheet of liquid just below it will be flowing with a velocity of v minus d because velocity is decreasing as you go down. You've seen that pattern of velocity as a function of y as you're going down. So this is at a depth of y. Okay. So this top layer will experience, or this surface on top will experience a viscous force in the backward direction. So viscous force, oh sorry, this will experience a viscous force in the forward direction because the layer on top of this is going at a higher velocity. So whereas the sheet, the surface below will be experiencing viscous force in the opposite direction. So when you consider this layer in between, its top surface is experiencing a viscous force like this, and its bottom surface is experiencing a viscous force like this. Okay. So consider a thin sheet of fluid at a depth y of surface area E, but thickness E1. So the magnitude of the viscous force acting, that will be equal to, so we can just write like this. This will be directly proportionate to the velocity gradient and also directly proportional to the area, the product of these two things. And the constant of proportionality is the material property which we call coefficient of viscosity. So this is the drag force or viscous force on a surface of area A. Okay. Such that the velocity gradient perpendicular to the surface. So the surface is in the horizontal plane and the velocity gradient is vertical. In this case, the surface is parallel to the xz plane, which is a horizontal plane. And this is the vertical, so not pressure, but vertical velocity gradient. So that is the viscous force. So here, eta, this is the Greek symbol eta, and n with the longest. Okay. So eta is called the coefficient of viscosity, and it is a material property of the given fluid. So the dimension of eta is dimension of force into time divided by area. Or eta is measured in a unit called poise, where one poise equals to 1 Newton second per meter square. So this is the empirical formula, in other words, experimental formula. Yeah, in this kind of laminar flow, Jagannath, velocity decreases linearly because we are having a uniform gradient. So if the rate of change is uniform, that means the quantity is linear with respect to the vertical. So something has gone wrong here. This is poise, okay, P-O-I-S-E. One poise being the SI unit is 1 Newton per meter, Newton second per meter square, or is the same thing as 1 Pascal second. Because Newton per meter square is the same thing as Pascal. So in common language, we say it is the unit of viscosity, but it is actually coefficient of viscosity. So unlike coefficient of friction, coefficient of viscosity is not a dimensionless quantity. It has a dimension and a unit. No, it is not a ratio, na, Shikhar. You can see if you just check the equation here, left hand side is in newtons, right hand side is coefficient of viscosity into area into velocity by distance. So it's not the ratio of two quantities which are, it's not eta into something which has dimension of force. No? Like in case of friction, the frictional force was coefficient of friction into normal reaction. So normal reaction has same dimension as force. Hence the coefficient of friction is dimensionless. In case of relative density, it is density of a liquid with respect to density of water or divided by density of water. So it is dimensionless. No, but here it is not a dimensionless coefficient. Okay, so not all coefficients are dimensionless. For example, temperature coefficient of thermal expansion, alpha, is not a dimensionless quantity. It is in per degree C or per Kelvin. Similarly, Young's modulus of elasticity is something we studied recently. It's not dimensionless. So like that here, eta is also a material property, which is a coefficient which is not dimensionless. No. Rakshit, coefficient of rigidity is different, better. Coefficient of rigidity is to do with that ratio of, actually that is modulus of rigidity. Viscosity is different from rigidity. For rigidity, we define the term modulus of rigidity, which is the ratio of shearing stress to shearing strain. And coefficient of viscosity is the property of a fluid which has to do with viscous force acting within it. Oh, yeah, we use the same symbol for it, that's correct. But they're different things. Okay? And hence, even the units are different. Modulus of rigidity, which we had seen in shearing stress and strain, has the unit of Newton per meter square, force per unit area. This has the unit of Newton second per meter square or Pascal second. Okay. So yes, unfortunately, we use the same symbol, but it is not the same thing at all, right? That is modulus of rigidity, which is defined for solids. Okay. For Hooke's law with respect to shearing stress and strain. And this is coefficient of viscosity defined for viscous fluids. So I'll just, as an example, I'll give you two very common values. Coefficient of viscosity of water, okay, at 27 degrees C or around about room temperature. So that is given by the value, I think it is around very close to 1, 0.83, yes, 0.83 millipascal seconds. Just let me clarify 1 second. Sorry, 0.85. It is equal to 0.85 millipoise or 0.85 into 10 raised power minus 3 poise or Pascal second. Whereas coefficient of viscosity of air, atmospheric air, at again about room temperature is much less. It is about 1.85 into 10 raised power minus 5 poise. So again, you don't have to memorize the value, just to give you a reference. Where something like turpentine oil or castor oil or something will have a higher coefficient of viscosity compared to water. Like coefficient of viscosity may have a bearing on like density, but at the same time, it's not necessary that if one liquid has more density than another, it must have a larger coefficient of viscosity. It also has to do with the nature of intermolecular bonding, and typically where there are polar molecules or there's hydrogen bonding, etc. Those factors will also affect. So yes, density is a way of understanding what affects coefficient of viscosity, but it's not the only factor. So just by comparing the density of two liquids, we cannot say for sure that which one has the higher coefficient of viscosity and which one has the lesser coefficient of viscosity. And viscosity is temperature sensitive also. So for the same material at different temperatures, the viscosity will be different. The coefficient of viscosity will be different. Okay, so let's look at an example of a numerical application of this. So for example, suppose we have, maybe a sort of thin block of sheet of plywood or something, or even a thin sheet of cardboard or something which is floating on water. And the water is completely still. So assume the water is completely still. And the total depth of water is known to us. So this is in a water tank or something. So below we have the floor of the water tank. It's a rigid surface. There is water up to a depth of h. And this is, let us say, a cardboard sheet, which is of surface area E. So basically you have, like, the three-dimensional situation would be something like this. You have a thin sheet of cardboard kind of floating on a water surface. But let's say this water is in a tank. The tank has a depth h, something like this. Okay. So now what we want to do is we want to make this move at a certain constant velocity. So we have to apply some external force. So find the magnitude of external force needed to push the cardboard sheet at a constant speed of V0. Okay. So for this, given to us is that, first of all, the coefficient of viscosity for water is, let's say, 0.9 millipoise. I've just rounded it off, or maybe I've taken it at a different temperature. Okay, and the surface area of the cardboard sheet, that is, let's say, maybe 2 meters square. The depth of water is 50 centimeters. So how we'll do this? So basically, now when we are considering the viscosity of the water, it's become equivalent to a situation which, with respect to solids, would be that if you have a solid block placed on a rough surface, on a rough horizontal surface, to keep it moving at constant velocity, we would need to overcome the kinetic friction. We would need an external force to balance the kinetic friction so that it does not decelerate. So this has become an equivalent of that. But instead of kinetic friction, the force is viscous force or drag force. Okay. So what we'll have to do here is we'll have to assume that as the cardboard sheet is moving at a velocity of V0 like this, okay, the velocity gradient of water under it is like this. It's a uniform gradient. Hence, there's a viscous force acting on it, which has to be balanced by external force so that its acceleration is zero. So this is like effectively the free body diagram of the cardboard sheet. So that viscous force will be coefficient of viscosity into area of the cardboard sheet in contact with the water below, multiplied by the magnitude of the velocity gradient, where I'll take this direction as my y-axis. So we can see that the velocity gradient here will be such that it's like this. That's okay. So now the formula becomes very simple to apply. As the magnitude of the velocity gradient. So it's 0.9 into 10 raised power minus 3 in SI unit, okay, into the area which is 2 meters square into this velocity gradient, which will, I have to give the velocity also. So let's say this velocity is 1.5 meters per second. So this will become 1.5 divided by 0.5. So this will give us the force in newtons. So 0.9 into 2 into 3 into 10 raised power minus 3 newtons. This is the magnitude of the external force we'll have to apply. Be equal and opposite to the viscous force.
इससे ज्यादा होगा तो ही वो मूव करेगा.
Sorry, come again, beta.
तो अगर इससे ज्यादा होगा तो ही वो मूव करेगा. Okay, like if I apply more force than this particular,
it will accelerate. If you apply more force than that, it will accelerate. Okay. Till again you have a new velocity at which the velocity gradient increases. So again the viscous force balances.
Okay.
You understanding now? While it is moving at this v0, if I increase the force, it will accelerate. But as it accelerates, the value of v changes now from v0 to a higher value. So again, it will come to a higher value at which it adjusts and reaches an equilibrium.
Okay.
You understanding now?
फिर से equilibrium कर लेगा ना sir?
Yeah, it will be what is called dynamic equilibrium. That is moving at a uniform velocity. So 5.4 millinewtons. This is the amount of force we need to apply on that cardboard sheet to keep it moving at a constant speed, in this case of this much, 1.5 meters per second. To keep it moving at a higher constant speed, we would have to apply a higher magnitude of force and vice versa. Okay, so just make a note of this. We'll discuss the next thing after that. But we have to maintain this constant amount of force to keep it moving at a constant velocity v0. Initially, let's say its velocity was 0. So to accelerate up to v0, you have to gradually increase the force. You understanding the point now?
Yes, sir.
But the moment the velocity reaches a value of 1.5, instead of increasing the force, we keep the force stable at that value. If we remove the force at that stage, then it will start decelerating because of the viscous force.
Okay, sir. I understand.
So just visualize it like a situation like you have a block at rest initially on a rough surface. So you have to increase the force gradually till you reach a constant, till you reach the velocity you require. But the only difference is there, the force that is opposing you is a constant force of mu mg, or kinetic friction coefficient multiplied by mg. Whereas here, the force that is opposing you will grow with the amount of velocity as it's increasing. So the faster the object is moving, the more the drag force. It's proportional to the velocity, you can see. Because ultimately the velocity gradient is v0 by h, where h is the depth of the liquid. So assuming that the depth is remaining constant because we're in a uniform kind of tank of water. So the faster I want to make the object move, the more amount of drag force I have to overcome. So that's how it is different from friction.
Yes, sir.
So this is one important situation in which we observe viscosity, okay, and we apply the above formula, which is basically that viscous force acting on a surface is coefficient of viscosity into surface area into the magnitude of velocity gradient across that surface. What I mean by across that surface is whatever the plane of that surface perpendicular to the direction of that plane, उस perpendicular direction में भी जो भी gradient होगा delta v by delta y, if you take the y-axis perpendicular to the surface, then the magnitude of that gradient. Okay, so that is the amount of viscous force. Now, a second situation in which we observe viscous force is when you, instead of looking at laminar flow of a liquid, where layers of liquid are slipping on each other because of velocity gradient, instead of that, you're looking at a situation where a liquid is at rest, but a solid object is moving inside it. Okay, like an object in free fall inside a liquid. If you take a heavy object which is having more density, like a metallic block or a rubber block or something like that, and just place it inside a liquid or place it on the surface, because of gravity, it will just fall. But as it falls, you will notice that its acceleration reduces. It doesn't have a uniform acceleration like acceleration due to gravity in a vertical free fall situation. And typically, if the liquid is highly viscous, then this is very noticeable, that its acceleration starts reducing till it achieves something called terminal velocity. So that is the second situation in which we will observe the property of viscosity. So viscous force or drag force acting on a solid object moving inside a viscous fluid.
Sir,
Yes.
sir, viscous force will depend on different objects, right? It will vary for different objects.
Yes. So in this case, the coefficient of viscosity is a property of the pair of materials, the material with which the solid is made, as well as the material with which the liquid is made. Okay. Or you could even have a droplet of a heavier liquid moving inside a lighter liquid. Like you have kerosene oil and you put a drop of water on top. So that drop of water will sink because water is heavier. Understood the point? Huh?
Yes, sir.
So the coefficient of viscosity that we'll write in this case, it will depend on the pair of materials. A droplet of water in kerosene will experience a different coefficient of viscosity compared to, let's say a small rubber object which you placed on kerosene. So that rubber object is going to fall because of gravity. So they will have different amount of viscosity. So viscous force acting on a solid body moving inside a non-ideal fluid. So viscous fluid basically.
Sir, for J, we have only sphere ka viscous force.
As a formula, you have only sphere, but you can have a general idea of any shape. Okay. So if the solid object is of any particular shape, moving inside a viscous fluid, we don't have the exact formula for it, but we have a general understanding of it, that if, for example,
So
at the given instant,
we can make a rough predicament.
That we know its properties. Okay, that if this is the direction of velocity, then two things we can predict. One is that the direction of viscous force will be exactly opposite. So as a vector, viscous force will be what we call anti-parallel. or opposite, or its unit vector will be negative of the unit vector of velocity.
Yes.
And the other thing is that the magnitude of the viscous force, this will be proportional to the speed. Okay. It will also be proportional to the coefficient of viscosity.
Yes. Sir.
But this time, this is for the pair of materials. Okay, that is both the material of the fluid and the solid. Okay. And it will depend on some other geometrical factor. Okay. So you can see that viscous force as a vector will become negative of some constant times v. Negative because the direction is opposite. Okay. Now that constant will be equal to coefficient of viscosity into some dimensional parameter. Dimensional parameter is basically some parameter with dimension of length. So for example, it could be the side length of a cube for a cubical body, or radius of sphere for a spherical body, and so on and so forth. How we know that this dimensional parameter will have the dimension of length? It is because you can see that by this thing, by units and dimensions. You can see that this constant
Yes.
should have the dimension of force divided by velocity.
Yes. Sir.
And we've already seen that coefficient of viscosity has the dimension of force per unit area into time.
Sir,
Yes.
so this C has any name?
This is called the drag coefficient.
Drag coefficient. Okay.
So C is called the drag coefficient. Okay. Now for a particular controlled experiment involving a spherical body, a solid spherical body, there is an exact formula for C which comes from experimental analysis. And that formula is called Stokes Law, as you might have heard.
Yes, sir.
Okay. Stokes Law was a major part in the this thing experiment also, the Thomson's experiment for E by M ratio.
The
Sorry,
Millikan oil
Millikan's
drop.
oil drop experiment.
Ah, Millikan oil drop.
Thomson's experiment was for value of E.
Yes, sir.
That's also a very famous experiment, but Millikan's oil drop experiment is very well-known experiment. So in that, to bring the oil droplet into a situation where it is moving at a uniform velocity, one of the forces in play is the viscous force. Of course, there's magnetic force, electrostatic force, all that also. So you will fully appreciate the physics behind Millikan's oil drop experiment in a couple of more months by the time you've done magnetism. And you'll be able to understand all the formulae involved. Okay, so this is the general formula that C is some kind of constant which is called the drag coefficient. Okay, and that constant depends on the viscosity of the liquid solid pair, and also some kind of dimensional parameter which has the dimension of length, and that has basically got to do with the size of the solid object. Okay, so this dimensional parameter is basically something that is affected by the size of the solid, affected by both the shape and size. the solid body. So in aerodynamics also, drag forces play a very major role. You might have heard of a special shape called an aerofoil, which is
Yes.
a shape to minimize drag forces, which is basically the shape of any wing or tail of an aircraft. It's specially used to generate drag forces in such a way that it creates lift, but it does not create dissipation of kinetic energy. So it's a combination of Bernoulli's concept or Bernoulli's equation, which is used to create pressure difference by creating flow of fluid, as well as drag forces. A combination of these things is used to create lift,
So
which can
even while
counterbalance the
an
weight.
aircraft takes off, we can also see that air which is turbulence जैसा create होता है sir wings पे.
Yeah, I mean,
वो दिखता है sir कभी-कभी. Like I
it
have
is,
noticed it.
it's not just during takeoff also, like during cruise also,
Landing also.
but it is more evident during takeoff because that is when the
Yeah.
lift forces are maximum.
Lift force, yes.
Like even when the aircraft is cruising at an altitude, there is lift generated because something has to balance the weight, but it's only
Yes.
balancing the weight. Whereas during takeoff, there is a high amount of acceleration upwards.
Yes.
So, with the physics of fluid mechanics and also viscosity and drag forces, with that background, if you start reading a little bit about aerodynamics and aeronautical engineering, like the basic principle of aeronautics, you'll clearly be able to understand the physics of mechanized flight.
Yes.
Whether it is coming from propeller driven design or jet aircraft or whatever it is, or even for gliders, how that lift is generated by the natural air currents. So we'll probably start understanding the physics behind it. Of course, interestingly, the pioneers of aeronautics, the Wright brothers, they were not physicists. In fact, they were more like mechanics who were mainly involved with construction of toys.
They're working in
most
cycle
toys.
mart, sir.
Cycle parts and toys.
Yes.
But they had deep interest in physics from an experimental point of view.
Yes.
And that's why experimenting with various mechanized toys, etc., they developed the principles of aerodynamics that was required for. That's also one of very interesting stories historically of how they overcame all the challenges that comes across designing something like that. In other words, they discovered the secrets behind designing aerofoils and being able to generate lift, the proper wing design, the wing to body weight ratio, all these things. So they did all that from experimental point of view. Okay, anyhow, so now we come to what is called Stokes Law. So Stokes Law is an sort of exact empirical law that tells us the value of this constant C for a perfect spherical body. Okay. So for a spherical body moving inside a fluid, the drag force or viscous force is given by an exact formula.
6
If we
pi
write it
nu
as
6 pi nu
6
RV.
pi eta, sorry, 6 pi. Yeah, so the factor 6 pi is dimensionless, eta is coefficient of viscosity, and R
Radius of the
is
sphere.
the radius of the sphere. Yes. Okay, so you can see that earlier we were talking about the drag coefficient being, coefficient of viscosity into a dimensional parameter. So in the case of a sphere,
Yes.
the dimensional parameter is 6 pi R, where 6 pi is just a dimensionless constant, and
Okay.
R is the radius. Okay.
It's
So R
basically
is,
derivation from the viscous force equation.
yes.
Okay.
Okay. Like actually both the general viscous force equation as well as Stokes law, they are derived from empirical data from experimentation. You understand? And there's no way of theoretically proving why this constant should be 6 pi r. Okay.
Yes, sir.
But by repeated experiments, statistical analysis of the data, so that is called the empirical method. Okay. So by that, it was established that the constant of proportionality has an exact value of eta into 6 pi r. So r is the radius of the sphere, and of course, eta is the coefficient of viscosity, as we know.
Yes.
Okay, sir.
So here V is not a terminal velocity, right?
V is not the
Terminal velocity.
what velocity, beta?
Terminal velocity.
No, V is simply the velocity of the spherical body.
Okay, okay.
You know, as it is moving inside the, it's assumed that the fluid is at rest. You know, so V is the velocity with which the body is moving inside the fluid. So V
Yes.
is the instantaneous velocity.
Okay.
Of the solid sphere. Okay, so from this we also observe the phenomena of, if we look at free fall of a spherical body in a viscous fluid or inside a viscous fluid. So we'll observe something very interesting, that there is an interplay between three forces: gravitational force, buoyant force, and viscous force. And out of these three, two of them are fixed in magnitude and direction. That is buoyancy and gravitational force. But the viscous force is something that varies. So as the body accelerates because of gravity, or as the spherical body picks up speed as it's going down, the drag force increases further and further. So it reaches a situation where the drag force is able to balance the difference, the apparent weight, you can say, which is mg minus buoyant force. So the moment it happens that way, that the drag force is balancing the apparent weight, the body is no longer accelerating. So it reaches what is called a terminal velocity. Terminal means final. Okay, so it's like it's not accelerating anymore. The speed stops increasing. It reaches a terminal or a constant velocity. So long back in relative motion, you would have heard the term that rain droplets are falling at a constant velocity with respect to Earth. And you might have wondered at that stage, how can something be in free fall and moving with constant velocity? Well, that's because the coefficient of viscosity between air and water is pretty high. So rain droplets achieve the terminal velocity pretty early in their motion, right from the clouds to the ground. In fact, there's an estimated calculation that if viscous force had not been there, then your average rain droplet would have reached the ground at a velocity of something like 10 to 11 times the velocity in reality. So at that kind of velocity, rain droplets would have a momentum which would make them rather lethal. So people could get injured if being hit by the ordinary rain droplet. So it's ultimately viscosity which saves the day. In the absence of viscosity, rain droplets would have been much faster moving projectiles, and therefore could have had enough momentum to cause serious physical injury. Yeah, so let's look at the situation of, let's say this is some fluid which is viscous. And inside this fluid, let's say now, we just drop a solid sphere initially at rest. So at t equal to 0, the solid sphere has been dropped over here. So its initial velocity is 0. So solid sphere which has radius, let's say r, and density of the material of the solid is rho. Okay. Now the viscous fluid has density equal to rho L, let's say. Okay. In fact, let's make this rho S because it's the density of the solid, is the density of the liquid. And also eta is the coefficient of viscosity for that particular solid liquid combination. So what we'll observe at t equal to 0, if the solid sphere is dropped from rest. So immediately when we drop it from rest, at that moment exactly, just for that instant, there won't be any viscous force acting because velocity is 0. So there are only two forces acting on it. There is buoyancy and there's mg. So it has an initial acceleration, let's say a0. So a0 will be equal to mg minus buoyant force divided by mass. Okay. This is at t equal to 0. So you can see that will become density of the solid minus density of the liquid into 4 by 3 pi r cube into g divided by, yes. Yes, beta, what's it out? Tell me. So the acceleration will be how much? 1 minus density of liquid divided by density of solid into g. Okay, Devansh and Rakshit, I'll scroll up and show you the Stokes Law formula once more. Then we'll come back to this application of Stokes Law. This application will basically lead us to the formula of terminal velocity concept.
Sir,
Yes.
I just wanted to ask you, will the terminal velocity equation differ for body free falling in air and a body free falling in a liquid?
Yes, because that coefficient of viscosity will be different.
Yeah.
So when we develop the formula for terminal velocity, you'll see it depends on all these factors. Actually, two things. One is the density of air is different from the density of liquid.
Yes, sir.
Density of water. So this term will be different. This rho L term will be different, and the eta will also be different.
Okay.
Okay. So the same body will have a very different terminal velocity, and not just terminal velocity, but how much time it takes to achieve terminal velocity. From the time you drop it till the time it achieves terminal velocity, that time will also be different. Okay, and the value of terminal velocity will also be different.
Okay.
So typically in water, the terminal velocity will be less, yeah? Because the density of water is also more. The coefficient of viscosity is also going to be more.
It's also more, yeah.
So
That's understood, sir. Yes.
Okay, so now, so this is the initial acceleration. Okay, this is the initial acceleration at t equal to 0 when we just drop it. Okay. Now, if we compare this situation to after some time, so by now, because of acceleration, the body has picked up some velocity. So its instantaneous velocity downwards is v at this moment. So now you see immediately along with buoyant force, it's also got drag force acting on it. It's got a combination of three forces acting, and its acceleration, let's say, is still there, but this acceleration will be less than a0 because there's an additional force. Okay. So this is at some instantaneous time. So at t equal to t, if v is equal to v, then the net force acting on it will be mg minus buoyant force minus viscous force. So that will be equal to mass into acceleration. So you see that this is density of solid minus density of liquid into 4 by 3 pi r cube g. So this term is basically this whole thing. This whole thing is this. This is like the apparent weight minus viscous force, which is 6 pi eta r into v. That is equal to your mdv by dt. or we can write the equation that dv by dt, that is its acceleration, is equal to this. And further, we can see that m is also density of solid into 4 by 3 pi r cube. So its instantaneous acceleration, or dv by dt, is going to be 1 minus rho l by rho s times g minus this factor 6 pi eta r upon 4 by 3 pi r cube rho s into v. So notice that this factor is nothing but the initial acceleration. So the acceleration is a naught minus, now I'll just call this a coefficient beta, we'll resolve it later, into. So this is how the acceleration is varying with velocity. So acceleration is reducing as v is increasing. Okay. Or dv by dt is equal to a naught minus beta times. Okay. Now that term beta is this thing. It is 6 pi eta r upon 4 by 3 pi r cube density of solid. So that is how much now? That is 9 by 2, okay, eta upon r square, 4 by 3 pi r cube into density of solid. So that is the factor beta. Beta is 9 by 2 coefficient of viscosity upon r square into density of the solid. So we'll make use of this term beta later. And a naught we've already written. Relative density of the liquid with respect to the solid times g, which is basically the initial acceleration also. So this is what we call the kinematics equation for it. That the acceleration is varying with velocity. This is the kinematics of it. It's the A versus V relation. So if we integrate this relation, we'll get V versus time. dv by dt is a function of V. So if we cross multiply and integrate it, just think in terms of kinematics. It's a one-dimensional motion where dv by dt is some kind of function of V. So from that, how we can predict the motion by integrating it. Okay. Yeah, beta is also experimentally determined because obviously it depends on coefficient of viscosity, density of the solid, and the radius of the sphere. So it's completely controlled in the experiment. So now coming back to this, before we go on to solve for v as a function of time, we can understand one thing, that when the sphere reaches what is called terminal condition, so that doesn't mean it's going to die. Okay, it's not medical term, it's a physics term here. Terminal condition of motion, not terminal condition of life. Okay, that means its acceleration becomes zero and its velocity becomes uniform, and that is called the terminal velocity. So that we can solve without integrating itself. We can see that v is equal to this terminal velocity when dv by dt or a is equal to 0. So just apply that condition. So a naught minus beta into terminal velocity should be 0. So the formula for terminal velocity just comes out to be a naught by beta, which you can see is 1 minus density of liquid by density of solid into g, divided by this factor beta, which we just now saw is 9 by 2 eta upon r square into density of the solid. So when we write this out properly, this terminal velocities formula comes out to be like this. It comes out to be 2 by 9 r square into density of solid minus density of liquid into g divided by eta. So there's no need to memorize this terminal velocity. We just need to keep in mind that v is equal to terminal velocity when acceleration is 0, or in other words, net force is 0. So in other words, mg minus buoyant force minus viscous force should be 0, or mg minus buoyant force should be balanced by viscous force. Okay. So density of solid minus density of liquid into 4 by 3 pi r cube into g should be balanced by 6 pi eta r into t. So this is the terminal velocity. So this will just give you this. So don't need to memorize it in a complicated way. You can just keep this concept in mind. Just keep this concept in mind. It's very easy to quickly relate that with this and from that to this. Okay. Whereas, of course, we will also integrate the above equation for dv by dt to get v as a function of time. But if we are just interested in calculating the terminal velocity, that will come from this directly. Okay, so you will be familiar with this terminal velocity formula, I think. maybe from chemistry also, but it comes from this application. Now we will come back to this to calculate V as a function of time. So now separately, to find instantaneous speed, as a function of time. So for this part of the derivation, we start with this, that dv by dt is a naught minus beta v. Okay, where we know the value of a naught, we know the value of beta. So the value of 9 by 2 eta upon r square into density of the solid. Okay, so we cross multiply and integrate. So dv upon a naught minus beta v is equal to dt. So now we can integrate this relation. And we can even do a definite integration from t equal to 0, initial velocity over 0, to some time t when the instantaneous velocity is v. So now we'll use this integration. We know that integration of dx by x is ln x plus c. So integration of dx upon a plus bx is 1 by b ln a plus bx plus c. So if this happens to be a negative constant, then there'll just be an extra minus sign here and an extra minus sign here. So that's what's happening here. We minus 1 by beta ln of a naught plus, sorry, a naught minus beta v limits 0 to v is equal to t limit 0 to t. Okay. So next step, we'll just put the limit, and with that we'll be able to complete the solution of this.